Welcome to section 1.3. We're going to be focusing on comparing decimals and ordering decimals, looking for decimals between decimals. So we're really going to dive into numbers that were expressed in the decimal system. We're going to be using our understanding of base 10 in order to build on the understanding of decimal numbers. One thing that may be helpful is to look back to our bundling example where we're representing decimals in bundles and how the value of the decimal and the place values where the digits go is actually defined by how we define that one toothpick or that one paperclip. So kids, when they learn something new, they will often try to bring understanding that they have from other areas, from other parts of mathematics, and use that understanding with adaptations or not in a new situation, especially if they don't have experience in analyzing the new situation and problem solving within it and making sense of it. So there are 5 of such preconceptions, knowledge from prior experiences that students try to bring into work with decimals, and especially comparison of decimals, that are very common. So the 5 that the textbook gives us are whole number thinking, column overflow thinking, denominator focused thinking, reciprocal thinking, and money thinking. Kids, when they see decimals, they often try to use one of these types of thinking in the situation with decimals. And certainly it's not going to give them the full understanding, but often it doesn't even get them the correct answer. So what I would like you to do is read through the 5 different ways of thinking, and then use some of the numbers that are in this box as examples for explaining the different types of thinking. So what I'd like you to do is in the questions that are going to come up, I'd like you to imagine that you are a student who has this kind of thinking, who is exhibiting this kind of thinking. And I'd like you, from the point of view of the student, compare 2 numbers from the box and explaining it with that kind of thinking. So for example, the whole number thinking, I may choose to compare numbers 2.1 and 2.793. And I'm going to explain as a child why I think 2.793 is bigger than 2.1. Whether that is actually a correct answer or not, I'm more focused on the explanation of the thinking. And then for column overflow thinking, I may use 2.5 and 2.21 as my examples. Again, I'm going to write out the student thinking, the student explanation of why they think one is greater than the other. We'll do each of these 5 in order. So first, we'll start with whole number thinking. Now let's look at an example for column overflow thinking. Now an example for denominator focused thinking. An example of reciprocal thinking. And a student's example for money thinking. Now, once we understand that decimals can be represented as bundled objects, and we try to make sense of those decimals, we need to keep our language consistent with that kind of thinking. So let's take a look at decimals between decimals, and let's see if we can use stuff we've already thought about, or ideas we've already thought about, or things we've already learned to make sense of these. So for example, contemplate the questions in the following paragraph for a few minutes before you continue with the rest of the activity, and then return to these questions at the end. So there aren't any whole numbers between 2 and 3, but there are plenty of decimals in between 2 and 3. If you're given 2 decimals, will there always be another decimal in between the 2? Are there some decimals that don't have any other decimals in between them? So for example, these are the questions that we need to be contemplating as we go through these activities. If you're given 2 decimals, will there always be a decimal in between the 2? And are there some decimals that don't have any other decimals in between them? And we'll come back to those questions. Question 2 says, work with a partner. Take turns giving your partner a pair of decimals and challenging him or her to find decimals between your pair. So what I would like to do is I'm going to try and stump you. And I would like you to answer the questions and how you were able to figure out the questions. So for example, 1.2 and 1.4, that one is the one suggested in the example. That one is pretty straightforward, right? If we look at it on the number line and look at our tenths, we know that between 1 and 2 tenths and 1 and 4 tenths, there's got to be a 1 and 3 tenths. So there's that that number. But what if I wanted to know between 1.5 and 1.6? So that would be a situation where these are consecutive tenths. So how would you figure out if there's another decimal in between those two numbers? Throw some ideas down into the question that follows. One of the ideas is that if those are tenths tick marks, I can zoom in and introduce hundredths tick marks. These are tenths. So there are lots and lots of numbers that I will now be able to write in between them. And notice that our explanation is another way of looking at things we've already done in the previous section. So this is directly related to what the kids already understand and know how to do. But what if it's 1.53 and 1.531? Take a look and see if you can come up with an example where you would be able to write a number in between those two numbers. And then make sure you write your answer in the follow-up question. So decimals between decimals on the number line. Now this is going to take us even further into the kinds of examples that I've just given you. So let's go through them now. If any of the examples up above didn't make sense, hopefully this explanation will make them make a bit more sense. We're asked for each pair of numbers that follow, find a number in between the two numbers. Label the longer tick marks on the number line so that all three numbers can be plotted visibly, distinctly. The labeling should fit the structure of the base 10 system and plot all three numbers. The numbers need not land on the tick mark. Okay. So if we have a situation where we have between 1.6 and 1.7, so we need tenths, right? So we could use the tenths tick marks. And in fact, these would be our adjacent tenths tick marks if our large tick marks were tenths. So then in between those, we would have lots of tick marks that we could use to label with hundredths. So this would be 1.61, 1.62, 1.63, 1.64, 1.65, etc., etc., etc. Okay, and you can pick any one of those numbers to be in between. Now, how could we use money to find a number between 1.6 and 1.7? Well, we would need to interpret 1.6 as money. 1.6 is $1.60, and 1.7 is $1.70. Now, what is a number, an amount of money that is between those two? And you can also find a number that would be meaningful there. So let's look at the numbers here. If we have the two numbers 12.54 and 12.541, now this first number is 54 hundredths, and the second number has 541 thousandths. So right now, the way they're presented, they're not falling on the same tick marks, right? One is the thousandths and one the hundredths. So we could label 12.54 here and 12.541 there, and then look for a number in between. That would absolutely be possible. That's one of the solutions. Okay, that is solution A. But there's another way to think about this. What if we wrote these two numbers and interpret them both as thousandths? So wouldn't it be possible to say that this is going to be 12.540 thousandths, and the second number would be 12.541 thousandths? Then, instead of placing them this way, we would be able to place them on two adjacent thousandths. And then we have a whole range of numbers in between that we would be able to identify. So for example, this would be 12.540 thousandths and 2 10,000ths. How about the two numbers 2.781 and 2.7342? Now the first number has 781 thousandths. The second number has 7,342 10,000ths. So if we were to try to label them as 10,000ths would we have enough space here? That's going to be a long way. So let's say 2.7810 ten thousandths. So 7,810 ten thousandths versus 7,342 ten thousandths. Now there are about 500 ticks in between those. 500 ten thousandths in between those. We don't have 500 ticks on this number line. There's just no way we'd be able to use these as 10,000 or even these as 10,000s. So if we don't, then could we use the smaller tick marks as thousands instead? Let's try to use these ones as thousands. So then the larger ones would be hundreds. If the larger one is hundreds, 2.73, 2.74, 2.75, 2.76, and 2.77. Not quite getting to 2.78. So that's not going to work. So let's try to get rid of this. So what if these are hundreds? And then large ones would be tenths. So if these are hundredths, then the large are tenths. So we'd have 2.7, 2.8. So if we were to zoom in and now try to plot these, 2.7, 2.71, 2.72, 2.73, etc. So 2.781 would be somewhere here. Very close to that, 2.78. And 2.7342 is going to be somewhere in the middle there. Okay, so we are able to plot both of these numbers. So 2.7342 and 2.781 by using the tenths as the large tick marks and hundredths as the small tick marks. So the numbers 23.99 and 24. So let's try to see if we can figure this out. Now, if we are going to use these as ones, let's see if that would work. So then that would be 23 and that would be 24. And then that number would be way over here, 23.9 and then 9. We could absolutely do that. But what if we wanted to make sure that that number falls on a tick mark? Let's see if we can do this in a different way. What if we use the large tick marks as tenths? So how many tenths are going to be in 23.99? So that's going to be at 23.9. And what's the next tenth? The next tenth is going to be 24.0. If we zoom in, our 23.99 would be right here. And finally, the numbers minus 1.9 and minus 2, if we make this minus 1.9 and minus 2.0, right? So the large tick marks are tenths. Then we have a whole bunch of numbers in between that we could be using. So minus 1.91, minus 1.92, minus 1.93, etc., and any one of those. And I'm going to leave number 6 for you to figure out. For a greater than or less than with negative numbers, explain in 2 different ways why a negative number is always less than a positive number. I will leave that for you. Now, you can use different models for this. You can use number line, you could use money model, you could use any model that you'd like. So Johnny says that negative 5 is greater than negative 2. Explain 2 different ways to explain to Johnny why this is not correct. I would like you to use the number line as one of your methods, and let's say money as the other method. But if you have a method other than money you'd like to use, you're more than welcome to it. Now, for each of the following pairs of numbers, write an inequality to show how the numbers compare, using the symbols of equals, less than, and greater than. A lot of schools use the alligator analogy here, but Alligators really have nothing to do with mathematics. And the alligator analogy, first of all, kids don't really remember. But also, it really doesn't make sense. And the kid needs to understand. It's like, oh yeah, right, the less than or equal to, that's the alligator thing. What was the alligator story and how does that relate to my math? So it's actually distracting them from what's going on. Instead, if you think of the number sign, the equal sign, that's when there's a balance between these two numbers, right? When the two things on the left and the right are equivalent. But if the number on the left is smaller, what we're going to do is we're going to bring these two ends together. And if we push those two ends together, then it becomes a sign like this. So that's the less than. But if we had an equal sign and this is larger, then we're going to push them apart. So we're going to have this sign. There's a further distance, a larger distance versus a smaller distance. Then we make a larger sign and we're able to write the inequality. So let's say for question A, -6 and -5.9, which is going to be further to the right or further to the left. The one to the left, if we start at 0, we're going to go past -5 to -6, going left. So -6 is actually to the left, and that's smaller, so we have a smaller distance in the equal sign, or it becomes a less than sign. B, -4.777 and -4.8. If we keep going, we're going to hit the -4.7, no matter how many decimals it has, before we hit the -4.8 to the left. So -4.8 is going to be further left, so it is smaller. Okay, and I will leave number C for you to do. Given the following number line, write inequalities to show how each of the pairs of numbers compare. So I'll take A, -r, and -p. So which one is further left? We don't even have -r on the number line. But we know that if this is r, that's how far we go to the right, then we need to go the same to the left to get the -r. So let's say now we have -r and -p, and -p is further left, so it's smaller. And I will leave B for you to figure out.